Well, our next speaker is Professor Upadrasta Ramamurty, but I call him Ram, and I think that's how you like to be called. And he's at the Nanyang Technological University in Singapore. He's been there about 5 years. He's a wonderful diplomat. His science is summarized beautifully in the paragraph below, but I want to tell you a diplomatic story. And that is, he came up to me and my wife having lunch yesterday, and he was smiling. And I could see that this was a bearer of news that we didn't want to hear, but he was doing it so diplomatically. He said, I don't want to destroy your lunch, but India has just thrashed Australia at cricket. So there's an example of his diplomacy. His science is great too. The talk is microstructural design of metals using 3D printing.
Thank you. Thank you very much. Thank you, Tony, for inviting me. This is my 4th or 5th time to Rasselheim, and I always enjoy it. I enjoy coming here. And so I keep asking Tony, when can I come next? Going after Mike to talk is like after Don Bradman has, gotten out and then going, so all the audience, you can leave because it's all downhill from here. There is also a small problem for me because in looking at all those wonderful slides and all the story, I forgot what I want to really say. So, but let me try to tell you a story here. So we are going to transcend from all that wonderful physics and how studies on water evolved into metals, really the very boring stuff. So I will try to tell you how we try to design microstructures using 3D printing, the new technology that is coming up for making structural components. Now, this conference or workshop is about advanced materials, and all of you know that the cornerstone of material science or designing materials is this, how processing affects structure and how structure controls properties. So this theme underlies a lot of talks. If you recall, Mohammad Edaudi's, for example, he was designing metal organic frameworks, and to capture different kinds of molecules, he was playing with the structure, right? The kind of porosity, the size of the pores that are there. The other talk, Rafael, I don't think she's here, talked about how structure processing affects the structure for battery applications and properties, right? So this is a common underlying theme for most of the advances that are made in material science. And in metals too, the fact that most of you flew or drove, etc., from far away from places was made possible because we understand those connections between processing and the microstructure and the properties. The properties here are mechanical properties in terms of structural reliability, stiffness, strength, toughness, etc. Okay. So we understand these connections in detail, and once we understand, we turn it around and say, if I want to design a particular component for a structural application, say a fuselage material for an aeroplane, what kind of properties I need, and in turn, what kind of microstructure is desired and how to process that. So this is something that has forwarded the civilizational aspects of our life. Now, so microstructures are plenty. There are lots of beautiful microstructures. You can see these are very few illustrations of those. So for example, go back a bit. So the jet engines that flew you here will have the superalloys with these kinds of microstructures. The fan blades most probably are made with this titanium, aluminum microstructure, etc. Right? So metallurgy, as probably most of you know, is the second oldest profession. So we all, understanding the microstructures and then translating them has been the part of our story. Now, microstructures can be controlled in 2 ways. One is by playing with the composition, right? So if you add carbon to iron, you get plenty of different kinds of microstructures that is possible, and everybody learns about the iron-carbon diagram. The second way to manipulate microstructures is during thermomechanical processing. So most of the metals are not just used in cast form, but in the wrought form, as we say, after processing them in like this. So in this process, what happens is, this is a cast, this is a cast alloy. So you can see that the grain structure, this is a super alloy, by the way. So the grain structure is very inhomogeneous, right? So what you need to do is break down that very inhomogeneous grain structure to make it more uniform. And what we do is, we use thermomechanical processing. So somebody mentioned about heat and beat technology. So metallurgy is, all said and done, a heat and beat technology, right? So what we do is we take the metal to high temperatures, beat it to refine the microstructure. So this is the way we homogenize, make it uniform, and refine the microstructure. Okay? So this is the conventional manufacturing of metals and alloys, and that's something that is very well understood. Now, what I'm going to switch over to is 3D printing. That is the emerging technology of metal component manufacturing, and how do we manipulate the microstructures in this context is what I'm going to talk about. So a little bit of introduction to 3D printing of metals. Essentially, the technical name for this is additive manufacturing. So the conventional manufacturing is often subtractive manufacturing. So you make a big casting of something, and then you beat it down to smaller sizes, and then you eventually machine to get the part that you want. Whereas here, we mimic nature in some ways. We build bottoms up, right? So typically, metals, in the metals context, the raw material that you are starting with is powder, okay? And metal powders require sufficiently high thermal input, so we use lasers or E-beams to melt them, okay? Now, what are the advantages of this? So if you take conventional manufacturing of metallic parts, it takes fairly large number of steps to get the final part, right? So this is true for any of the, most of the wrought products that you actually deal with in your day-to-day life. Whereas when you talk about 3D printing, you're printing the final part in one shot. So the chemists talk about one-part synthesis. Think of it like that, right? So you can build very complicated shapes in one shot. And it has a lot of advantages because now, the key advantage is if you make a prototype, you can actually test it very quickly. So instead of having to wait for several years, unlike Mike's one of those papers, you can actually get, have a new concept and make the part and test it out before you can really use it. That's the advantage. And the loss of material is also very small. Okay, so as the buy to fly ratio time is it can be reduced substantially. Okay, this is a great advantage in 3D printing of metals. Now there are a number of different techniques for 3D printing metals. As I said, often we use powders, and then the heat source can be an E-beam. For example, if you want to use a super alloy product, you use a E-beam. For most other cases, we use lasers. So this is what is called laser powder bed fusion. And that is what I'm going to focus mostly on. OK, so here is a quick movie. So what you do is you spread a layer of powder, right? And then you take a laser beam, and you melt the powder and fuse it wherever you want, right? So the part that you want to build, you have a CAD view of it, and it slides CAD design, and then basically you build layer by layer to make the 3D part. That's the key advantage, right? So at any instance here, you're essentially melting not even a line, a pixel by pixel, right? So the thing that happens is because you're melting the powder very rapidly, but it also solidifies very rapidly, right? Because it is sitting on a huge sink, heat sink. So as a result, the rapid solidification conditions prevail. Okay, the molten metal solidifies very rapidly. Okay, so this, let me go back again. I'm using a different, I'm not used to this. So you get essentially 10 power 6 kelvins per second kind of cooling rates that are possible. So we can exploit that, right? Let me give you an example of how we exploited it. So this is the example of equiatomic iron-cobalt alloy for soft magnetic applications. Okay, just a bit of a background. If you look at this iron-cobalt, if you have 50% cobalt, right, you get the best soft saturation magnetization and the maximum permeability, etc. So it's very good. Here is the phase diagram of iron-cobalt. So at high temperatures, it's FCC, phase-centered cubic. It gets into solid solution or disordered BCC, but the catch is here. So it essentially turns into B2. That is, you can think of it as an ordered BCC structure. Now, what's the problem with that? So by the way, the ordered BCC or B2 structure is the one which gives the best of these magnetic properties. But if you look at the ductility of that alloy, right? So here is okay? It's zero ductility. That means it's extremely brittle, right? Brittle materials are okay as plates, glass plates, and ceramic porcelain in your home. But if by accident you drop them, and especially if you're a young boy, your mother will give it to you, right? For breaking her precious porcelain, right? That's why we use mostly metals, because they are tough, right? So the advantage of all these great magnetic properties is compromised because this is zero ductility. It's very brittle material, okay? So you can't really do anything, mechanical operations on this material. Now, so the key way to do this is basically you want to retain the disordered BCC structure or solid solution structure. And if you want to do that, you have to go to cooling rates of the order of 3,000 degrees per second, right? So somewhere there, you will be able to retain the solid solution structure. Now, the thing is, if you want to get that kind of cooling rates in conventional manufacturing, you have to take the molten alloy and just splat cool it. You basically deposit it on a copper wheel that is turning around. What it then limits you to is 0.7 millimeter thick member or sheet or whatever, right? So you can't have more thicker than that because the cooling rate will be smaller than that, and then you will get the ordered phase, and that will be bad news from ductility point of view. Okay, so here we thought, okay, I have this intrinsically faster cooling rate that is available to me in the laser powder bed fusion, right? Can I exploit that? So we took this nearly equiatomic iron-cobalt alloy, and these are the powders, okay? And then we actually printed, you can see these are not 0.7 millimeter thick ones, but fairly large samples. And then we looked at the microstructures. The microstructures are typical of the 3D printed structures, but this is the one that is the precision electron diffraction pattern, scanning over a large area, and you can see that it's mostly BCC structure, right? So because of the intrinsic cooling rates, although we are building bulk parts, not thin membranes, we are able to retain the BCC structure, right? So now we do tensile test on these things, and we get fairly large amount of ductility, and that is represented here as a function of yield strength versus elongation. So if you take ordered alloy, you get zero ductility, no ductility at all. If you were somehow able to get thin sheets, even then it's not really great. But here we have fairly high strength because we have some ductility, and as a result, fairly good elongation as well. So laser powder bed fusion, or the 3D printing technique, allows us to essentially make bulk parts. But in the disordered, or not amorphous state, but in a solid solution state, the magnetic properties are not that great. So what you have to do is, you still have to get to the B2 phase, so you can do a heat treatment afterwards. And once you do heat treatment, you can see that now we got pretty much almost B2. There is still some BCC phase left, but this is how you can get the best of the both worlds. So you make the 3D printed part which has some ductility, so then you can do some machining operations, etc., which are inevitable. You can't, although you can print the 3D part finally, but you need to do some small machining, etc. And that's what you can do, and then heat treat this alloy to get these properties. So these are the typical magnetization studies. What you will see is that the saturation, magnetization, coercivity, and permittivity are best after heat treatment for this alloy. So the bottom line that I want to say is we exploit the intrinsic advantage that 3D printing enables us, in particular laser powder bed fusion, to get this combination of properties, which is ductility and better magnetization for making these materials. All right, this is a summary of those things. Now, I also mentioned that this is a bottoms-up building strategy, right? So this enables us to do mesostructural engineering, okay? You're essentially, at any instance, you're building things line by line, as you scan the laser along the lines, which are overlapping with each other, and then you build layer by layer to get your 3D part. This imparts a mesostructure to the material, right? So this is the mesostructure that I'm talking about. This is an aluminum silicon alloy. So if you look at the cross-section here, you can see each of this is basically a cross-section of the laser beam that has passed. And the top view, so by the way, they overlap. That's why you see that kind of thing. So it's a fully dense 3D part. Now, this is what I call a mesostructure, just to contrast it with the microstructure. And this mesostructure imparts interesting properties. So the mesostructure you can play around with by changing all these parameters. For example, you can see this, you can change the spot size, the spacing between the hatches, the layer thickness, and the scan speed, etc. Okay? So this is another mesostructure in an aluminum silicon alloy. By the way, in the cars, all the engines blocks typically are cast with this alloy, aluminum silicon. And it's also, the high tension cables are mostly made of aluminum silicon, this very alloy. Okay, so if you go back and look at this region hatch boundaries, they are decorated with silicon, okay? So the solubility of silicon in aluminum is negligible at room temperature. So aluminum doesn't like to retain silicon. Basically, it decorates the hatch boundaries like this. And so when we did tensile test on this, what we found is the strength has gone up a lot. So for example, if you take the same alloy and use make a casting out of it, that's what you will have in your cars as a material. It has about 100 MPa strength, 100 MPa yield strength, and 200 MPa UTS. But when you take the same alloy and 3D print it, the strength nearly doubles. Okay? And this doubling happens because of the rapid solidification. There is a microstructural refinement that happens, and there is also there is enhanced solid solution, because there is some silicon that gets retained within aluminum because you are rapidly solidifying, right? So typically, when we look at mechanical properties of materials, we talk about Young's modulus. All of you know the resistance to elastic deformation. Then there is resistance to plastic deformation, that is for permanent bending of the material, for example, permanent deformation. But the third property is toughness, resistance to fracture, resistance to cracking, right? This is also a very important property, right? So if you need all these three, and it so happens that if you take any class of materials, only two will be exceptional. The third will be poor. Polymers, for example, lack stiffness. Ceramic materials lack toughness. Metals lack strength, pure metals. That's why you don't use pure gold. You use 22 karat gold often, because you add copper to strengthen the metal, right? So we also know that strength and toughness they go in the opposite directions, right? So if you try to increase the strength, toughness often comes down. So we saw in the previous slide that when I did 3D print, the strength has gone up quite substantially. So the intrinsic or implicit assumption is that the toughness goes down. And in fact, if I look at the ductility, it has come down a lot, right? So this material, prima facie, looks very bad. It may not be useful at all. So we were also thinking that, but anyway, we did fracture toughness measurements. And by the way, this is Rob Ritchie has written a paper some years back that there's conflict between strength and toughness. So, and this is what, as materials engineers, we always try to, we want to both of the best of the both, but it's just if you try to increase strength, you get down on toughness. So when we measured the fracture toughness of this aluminum silicon alloy that is 3D printed, okay? So by the way, the benchmarking is with Ascast alloy, about 11 ampere root meters. What we were expecting it to be very poor, as brittle as glass, for example. What we found is actually the fracture toughness has gone up significantly, by 4 times, about 400%. So the reason this happened is because of these mesostructures that I talked about, right? So you have this highly decorated, silicon decorated boundaries. And the crack, what happens is it actually looks at it and it says, oh, there is an easier, softer path, or not softer, brittle path for me, easy to propagate, less energy consuming, and it dives through. But what happens in that process is it loses its driving force. So the analogy, let me give you, is, so if you have to bicycle from here to Waldorf, for example, it's all flat, so you may not consume too much energy. On the other hand, if it's a hilly area, right, the initial starting point and the final point are the same latitude or same height. But if it is a flat land versus like this, you know that you have to spend a lot more energy going through this, right? So what happens is cracks see initially an easier path, they dive, and from a fracture mechanics point of view, we know in detail that the driving force dives down, so you have to spend a lot more energy to get the crack growing. And that's what enhances the fracture toughness, and this crack tortuosity, we make essentially cracks life tortuous, and that's why this enhancement in toughness comes about. So in fact, you can see this through these images, the cracks get deflected quite considerably here. Okay, so from this part of the story, the thing is the strength enhancement comes about in 3D printed aluminum silicon because of the rapid solidification conditions, but the toughness enhancement comes because you have a mesostructure, reminiscent of the 3D printing strategy that you employed, and that you can play around with. Now, we switch over to another important aerospace alloy, Ti-6-4, titanium 6 aluminum 4 vanadium. So if you look at the big engines, the front blades are all made of these Ti-6-4, okay? And so how do we manipulate these mesostructures is what I will illustrate here. So for example, if we use a layer thickness of 30 microns and a scan rotation of 90 degrees, you get a very interesting, a square-shaped grains on the top. If you look at the top, you get this square-shaped grains. But on the side, the epitaxial growth conditions prevail. So what I mean is, basically, once I deposit a layer, right, the grains that are already there act as a nuclei for the subsequent layer. So the epitaxial growth occurs. So as a result, on the side, you get columnar structure. So if whatever the build height is essentially taking square bricks, square cross-section bricks, which are as high as your build thickness, and as if you're stacking them together, right? Now, if you change, you keep everything else the same, but change the scan rotation to 67 degrees, the epitaxy remains, but what you will get on the top is more, equiaxed grain structures. So the previous microstructure that I showed, people don't like it because it will introduce significant anisotropy in properties. People are worried about it, so we don't want that. So how do we break it? So one strategy is that, but here you still have aligned grains. So if now I change to 60 microns layer thickness. In the previous two instances, it was 30 microns. I doubled it. So epitaxial growth is lost, right? As a result, I get, so on the top, I still have the square grains, but in the side, I basically don't have the epitaxial growth. So these are no longer columnar grains. And when I finally go to 60 microns and 67 degrees rotation, I get equiaxed grain structure in the thing. So the last four slides, I hope you recognize that by playing around with the processing conditions, I could change whatever way the mesostructure evolves. So metallurgists would like to play God with the microstructures. We want to essentially design the microstructures the way we want. And what I illustrated to you is that by changing these parameters, I can get the kind of mesostructure that I want, right? So we tested a whole host of properties. They're okay. I will skip this. And because we are able to get equiaxed structure, we were able to get both strength and toughness. In this case, ductility combination, very good. But the rapid solidification in this case results in a metastable martensitic structure, the alpha prime structure in this case. That's what you can see here. And sometimes if you are thinking about a slightly higher temperature application, metastable structures are not desired, right? Because they can go into the stable structures and in the process relieve strains and the part can go out of shape. People don't like that. So we heat treated this alloy using, explored different options. I'll skip these. So you get, so maybe just since I'm following Mike, I have to also show you nice, beautiful pictures. You can see a lot of different kinds of microstructures. Okay, so we picked one of those heat treatment schedule on the basis because, for example, this is 2 cores, and we don't like that. So we picked, I think, this particular one, and then heat treated. This is a very busy table, but don't worry. So I'm sure all of you follow stock markets, Dow Jones Industrial Average. If you see green, that means stock price has gone up. If you see red, that means your cryptocurrency has gone through the bottom or whatever. So, because you all play in crypto, right? Okay, now, so when you see red, what it means is we gave up a bit. So in life, you can't have everything, right? You have to give something up to gain something. So our objective here was to gain on ductility and toughness, etc. Okay, so we were willing to give strength a bit. Okay, so if you just browse through, you see we gave up on strength about 10 to 20%. Okay, that's roughly what you will get. But we gained 50% in ductility. Most importantly, on toughness, we gained almost 100% in many instances. Right? So this is the heat and beat. We didn't quite beat here, but the heat, the technology we used to, so enhance the strength. And there are also the crack growth properties under cyclic loading, how these things move. So one is by playing around with the processing combinations, layer thickness and scan rotation, I could get different kinds of structures. And then I can also use heat treatment to enhance the properties. So this is the kind of things that you can do for microstructural manipulation of these alloys, right? So then there is also, you can also discover new alloys by rapidly screening. For example, we wanted to try out iron aluminum. So as you know, iron is fairly dense, and if you want to lighten iron-based alloys, adding aluminum seems to make sense, right? So because it's much more 2.7 grams per centimeter cube. But adding aluminum makes iron very brittle, and especially 3D printing may not be ideal. So what we wanted to see is the maximum aluminum content that would enable us to do crack-free fabrication, 3D print, and of course, look at the mechanical properties. So we built, this is done in collaboration with IMRE colleagues, a graded composition. And in this process, you can actually identify up to which aluminum content the iron can tolerate without cracking during 3D printing. Okay. So this is the iron aluminum phase diagram. So it has all kinds of phases, you know, FCC, BCC, obviously, and also intermetallics things. So one of the things that happens here is at the iron end, right, it's highly textured. So the grains are actually growing epitaxially like this. It's as illustrated schematically here. But once you go to a certain aluminum content, you get very fine grain structure. So the grain morphology changes quite dramatically as you increase the aluminum content. And this is, my time is really up. This is, the reason this happens is because of the constitutional undercooling, something that you can actually learn from phase diagrams. And I will skip this part. So, in fact, when we look at this constitutional undercooling and the growth constriction factor, you can actually see that they are fairly well correlated with the grain size and the growth constriction factor. All right, I have 3 minutes. So what I will do is I will skip. We also have been exploiting this directional growth of grains for electric applications. Iron silicon alloys are used in transformers, for example. These are laminated sheets, and we have been exploiting that 3D printing technologies. So we used iron silicon alloy. I'm just going to skip this very quickly. So we picked a specific composition, 3.5 weight%, and then we built these parts. And you can see these are highly textured. So for example, these are all 0, 0, 1. That is the easy orientation for magnetization applications. And so this is illustrated here. And then my colleague did simulations on these things. It's not an experimental one, but electric motor simulations. Let me just show you here. This is the last but one slide. So for example, iron loss is basically energy loss that occurs due to eddy current losses. And if you are using a 300 hertz, the iron losses, eddy current losses are pretty bad for the heat-treated 3D printed structure, and the overall losses are similar. But if you go to low frequency, 50 hertz, you can see that this 3D printed and heat-treated alloy really has very low losses. So some specific niche applications can be found for these technologies. All right, so I have 2 minutes left. So hopefully I illustrated to you that these 3D printing technologies are not just only technologies for manufacturing parts, engineering parts, but there is a lot of interesting science one can do. Right? I talked about phase diagrams, crystal structures, growth factors, and et cetera, right? So, which is chemists and physicists all should be anyway knowing in addition to metallurgists, thermodynamics and kinetics. So, in this process, we can actually do a lot of exciting science, but also think of products that really can be used in applications in aerospace, automobile, and all kinds of other applications, electrical, and so on and so forth. With that, thank you very much for your attention.
Thank you very much, Ram, and you made some sacrifices for the coffee break, which is rather thoughtful of you, I think. Has anyone got any questions that they would like to ask? Yes, we have one immediately here.
Hello, that's a very good talk. Thank you so much for that. Mostly these 3D printed materials are used like after post heat treatments. Like we can't use them like as 3D printing. So what's the effect of post treatment on the epitaxial growth, which you are mentioning?
Very good question. So most of the times we have to do heat treatment to relieve the residual stresses. So there is actually substantial residual stress in these materials. And let me just illustrate this. Well, I think they shut down already. Okay. In fact, there is sometimes so much residual stress when you cut the piece from the substrate, it'll just crack up. Yeah. So that's why we have to do heat treatment to relieve residual stresses. But if you do at temperatures, you don't allow the grains to grow. So epitaxial growth, basically in if you basically engineer it to obtain it during printing, then you can do heat treatments at sufficiently low temperatures so that it doesn't go away. In the case of Ti-64, there are instances where we go above what we call beta trances, and then all that structure is lost. So you have to pick the right temperatures to do these heat treatments.
And what's the maximum thickness which you achieved in this epitaxial growth?
Here, no worries. You can get as long as possible. So that's not at all a constraint. Okay, it's choosing the right composition and right combination of process parameters.
Right. And one more follow-up question that you have used continuous laser probably, which I'm assuming. You have used a continuous laser, which I'm assuming. So what if I changed the laser to nanosecond or femtosecond? Like how is it going to affect these microstructures, specifically the epitaxial ones?
I don't know that answer, but so laser is essentially used to melt the things, right? So there is whether we use the energy distribution, whether it's a Gaussian or a top hat. So there are other, for example, heat treatment. We can do after melting. We can have another scan where it's a little more mellower, so that you do the heat treatment in situ. Mm-hmm. Because what I don't mention here is not all metals are amenable for 3D printing. Most of them actually crack up. Yeah. So how do you really make them, print them without cracking and porosity is a key issue. Mm-hmm. So it's not so much about the laser beam, the kind of femtosecond or whatever. It's more how do you prevent cracking. That's the constraint we think of all.
Okay, thank you so much.
Thank you, yes. And we have one here.
Hello sir, it's a very nice presentation. So my question is, can you comment anything about the oxide layer formation? Because of this laser painting, so there is a very layer by layer painting. So each layer is very high to form the oxide layer. So how you prevent this formation to prevent the formation of oxide layer? And similarly, this oxide layer formation cannot prevent the epitaxial growth. It can't affect on the epitaxial growth of whatever you are told is the formation of the epitaxial growth.
We typically use an argon environment, flowing argon. It's not completely devoid of oxygen in the chamber, but we minimize. So that's oxygen pickup. Even in titanium case, it's not a big deal. It's not a big problem for us. So it's epitaxial growth occurs only under some combinations, as I said, illustrated in titanium case, it's only when you use a smaller layer thickness, right? And also, for example, if you take aluminum-iron case, right, or iron-aluminum case rather, you don't get epitaxy once you have a certain amount of aluminum because the phase diagram dictates it, okay? So oxygen or oxides influencing the 3D printing materials, printed materials characteristics is not really an issue for most of the alloys that we are dealing with. The powders themselves may have some oxide layers, but they generally never come into the play in most of the instances. So we do take good care of them, not to make sure that they don't oxidize when you're making them.
Yeah, if we do in the oxygen environment, but a normal environment instead of the inert environment, so definitely it will go to the.
That's obviously the case. But inert environment, if you use oxidizing environment like for aluminum powder, you can't even build. It's going to be actually major problems are then they will catch fire. The aluminum powder will catch fire, and you have some problems at hand. So these powder handling has to be done very carefully. There are a lot of other issues that one has to worry. So we were trying to do metallic glass powder 3D printing, and my student told me that even when you open it will catch fire. So you need to really worry about some of these things. Yeah.
We have a question from our leader.
Yeah, Tony.
Thank you, Ram, for a wonderful talk. This is a technical question, but you showed images with the iron-cobalt alloys, where you can map the BCC versus the cesium chloride structure. And I wonder, how do you do that when differentiating iron and chromium with X-rays is extremely difficult? What's the basis of?
This is basically the electron diffraction, selected area electron diffraction at the nano level. So they scan. Fengxia has done it. So somebody who's trained by you. So Fengxia Wei has done this work. So they actually take TEM and then they actually point by point, the precision electron diffraction technique. Okay. Yeah.
That's really interesting that you can contrast iron and cobalt with electrons, but not with X-rays.
Yeah, another.
But the diffraction pattern, if you have an ordered phase, you will get those extra peaks, right?
Yes, I get it. Yeah.
Another vote for the first talk. You want to ask one as well? I'll make this the last because.
Just have a question about the grain size.
Yeah.
And what the effect of grain size on the quality of printing? Do you like that to deal with smaller grains or larger grain to improve the quality?
So there is no one answer to this. The grain size. So typically we know something called Hall-Pitch relationship, which is basically finer the grain size gives you better properties, right? We would obviously like finer grains as much as possible. But in the iron silicon, for example, we would want grains to be oriented in a particular manner, right? So in those cases, we want as coarse a grain size as possible. So there is no one answer that fits all. Even when you look at the mechanical properties, coarse grains give you better fracture toughness, whereas fine grains give you better strength. So depending on the application that you're looking at, you need to pick these things. And one of the other things is typically we are optimizing for many properties, right? It's not just only strength, toughness, corrosion resistance, economic availability, cost of the things, availability of stuff. So there are a lot of things that we are simultaneously trying to optimize as a metallurgist, and that's the thing that we have to do. Yeah.
Well, that's been a very interesting discussion. Thanks, Ram. And I think I take away the fact that it might be okay to fly in a plane that has structural features engineered through your 3D alloy printing. So let's please thank Professor Ramamurty for a fantastic talk.